Okay, Alfred, let me turn it over to you, and we can start with the technical subject.
Okay, probably we should have a look at the last or at the March issue that was also distributed at the APEC show. And we have prepared the first question for you about this article, which discusses the benefits of using multi-level topologies and cascade configurations. So what are the main design trade-offs when selecting between these two approaches is my first question to Alex Lidow.
Thank you. And I'm also joined here by Alejandro Pozo, who might either correct me if I'm wrong or add to whatever I say. But we're, as engineers, we're very used to paralleling devices. So devices share current. With multi-level topologies, really what you're doing is, you're letting devices share voltage. And the advantage, of course, is that lower voltage devices have lower conduction losses or on resistance than high voltage devices. And in fact, if you put several devices de facto in series, they will have a lower overall resistance than the high voltage devices. And it yields a couple of benefits. One is higher power densities, and it also allows you to be more efficient. Now, for many years, this has been around, but only in the last few years has there been an ecosystem that can support this. And in particular, there are low-cost controllers. And thanks somewhat to Infineon also, there are low-cost isolated gate drivers and also low-cost isolated power supplies. So now the ecosystem is together where you can actually do multi-level topologies at a lower cost than two-level topologies. And that wasn't possible a few years ago. And so, something I had a dream of many, many years ago of using multi-level topologies to make our low voltage GaN compete with other people's higher voltage MOSFETs and GaN. It's finally coming true.
So how does it come true? So why hasn't it been possible before?
So there have been multi-level solutions for a long time, particularly in very high power, very high voltage applications, thousands of volts, where there's been no semiconductor that can reach thousands of volts. So it's not new, but it's always been fairly complicated from a control point of view and fairly expensive from an isolation point of view. And now you can buy very low cost isolated gate drivers and isolated power supplies to take care of the isolation problem without any trouble. And controllers like those made by Microchip are now low cost and high enough performance that they can do the control function, which is a little bit more complicated the more levels you have, and they can do it. And that's just software. Once you solve the software problem, you don't have to solve it again and again. It's embedded in the controller.
Okay, so it was the holistic approach, so to say, that enabled it.
The ecosystem finally caught up with an idea that's been around for many years.
Okay, I forgot something at the very beginning, because Alex, you are so familiar to almost the entire community. You're the CEO of EPC, Efficient Power Conversion, but I didn't introduce all the people who will be participating in our discussion today. For example, I didn't introduce Alejandro Pozo, who didn't switch on his camera so far, who is your colleague, and he's also one of the co-authors from the story that you provided to Bodo's Power Systems. So, Alejandro, I don't know exactly how to pronounce your name. Maybe you want to switch the camera on if you feel comfortable. If not, it'll be fine as well. So we will only ask Alex later on. But
hi, hello.
Hi.
Hi, this is Alejandro.
Yeah. Maybe you can start introducing yourself Alejandro, including saying your name, how to pronounce it correctly.
Yeah, so this is Alejandro. I'm part of the applications team with EPC, and yeah, I've been working on some of these multi-level solutions. And I think yeah, what Alex described about them was pretty accurate.
I think so, yes. And then we also have Frederik Dostal from Analog Devices.
Hello.
Frederik, maybe you can say hello and talk a little bit about yourself and your functionality at ADI.
Absolutely. So thank you for having me today. So my name is Frederik Dostal, and I'm a subject matter expert for power management. So what does that mean? Well, I work for our largest power management business unit, and I support power management applications here in Europe. And with supporting applications, what do I mean? Well, I support customers that have interesting power management opportunities for us for analog devices. I give technical seminars and write technical articles. And especially, I give lots of LT Spice seminars as a simulation tool that is quite popular amongst circuit designers worldwide. And yeah, and I've also worked with GaN devices, and Analog Devices has just released a few parts driving GaN switches, and so I guess that's why I'm invited today. Thank you.
Okay, thank you for being here.
Mm.
And the next member who is discussing with us is Johannes Schoiswohl from Infineon. Johannes, please introduce yourself as well.
Yeah, so my name is Johannes Schoiswohl. I'm at Infineon since I think 17 or 18 years, started in technology development, then application engineering. I was running various product lines, and since 2 years at Infineon, we formed the dedicated GaN business line when we acquired GaN Systems. And with that, we want to accelerate actually further gallium nitride within Infineon, but overall in the industry. That is my role right now. I'm running this GaN business line.
Okay, so probably I should ask you the first question already. That is tailored to you. We will put it on the screen. What are the key features and benefits of Infineon's 650-volt bidirectional switch, so the HVBDS products?
So maybe to start with, what is this bidirectional switch? Essentially, it's, I would say, the ideal semiconductor switch, as we might know on this call. Standard power switches or MOSFETs, they conduct, they can only block voltage in one direction, and in the other direction, the body diode typically gets flooded and the switch conducts. Now with the BDS, we have a switch that blocks voltage in both directions, and then a controlled way I can also turn on the switch in both directions. So it's a 4-quadrant operation mode. And that is really an ideal device because now you can realize a lot of nice topologies, which was also possible before by just using 2 silicon switches back to back, or also GaN switches or silicon carbide switches back to back. But the BDS monolithically integrates this into one device and is a very cost-effective implementation. So what we have been working on and what we will release very soon into full production, very soon means within weeks into full production, is the 650-volt GaN bidirectional switch. It's based on our GIT high voltage technology. It's not a Schottky gate, but the so-called gate injection transistor, where we feel, especially for very high power applications, this is a very suitable technology. And what is the benefits? Well, as already said, instead of using 2 switches, it's monolithically integrated into one switch. So you have simply fewer switches, fewer components on the board. It's GaN, you can then drive up switching frequency, you can reduce the amount of passive components or make them smaller. And it also increases then overall the efficiency in specific topologies. So that I would say is really the benefit, power density, efficiency, with this new kind of semiconductor device that so far we did not have in our hands.
Okay, thank you very much, Johannes. My next question goes to EPC, whoever wants to answer it. And it is, How does the lower figure of merit of low voltage GaN devices translate into real world efficiency improvements in power supply designs? Alex, either you or Alejandro.
I'll take a shot at it. So, figures of merit are really derived in order to give a shorthand way of comparing devices and getting a sense of how they'll operate. So there are many, many figures of merit. For example, there is the cost figure of merit for a device like a GaN device, which is the on resistance times the area of the device. It tells you how large the chip is. Smaller devices will nominally cost less. But there are figures of merit for almost everything. For example, if you're in a hard switching application like a buck converter, well, there's a hard switching figure of merit, and that tends to be the on resistance times the gate charge. And so that RQG product is another one. If you're doing a hard switching circuit, you can compare devices. Typically in a GaN device, the RQG product is an order of magnitude better than in a silicon MOSFET. For soft switching applications, one of the dominant factors is the output capacitance. And so for that, there's an RQOSS figure of merit. And that tends to be a factor of 2 or 3 better for a GaN device than a MOSFET. If you're looking at a figure of merit for a multi-level topology, like we talk about in the paper, then you need to use a combination of these. For example, I think the multi-level figure of merit is the square root of the RQG figure of merit squared plus the RQOSS figure of merit squared plus the RQRR figure of merit squared. What's that RQRR? Well, that's the reverse recovery time times the on resistance of a device, which in the case of GaN is 0. If you look at those 3 figures of merit and compare GaN against silicon in a multi-level device, the difference is close to an order of magnitude superior for GaN.
Okay, Frederik is smiling. So Frederik always thinks about how to drive GaN devices. Maybe you can contribute in that context as well.
Yeah, absolutely. Well, as a general point, I tend to like to smile, so I was not smiling anything specific, but yes, absolutely. I think wonderful new GaN devices have been released in the last few years, and I think a little bit of a bottleneck has been that the average user coming from using MOSFETs in their switch mode power supplies actually has the, let's say, the courage and all the tools to actually make the switch and evaluate GaN switches for an application, and then finally really use the GaN switches in mass production. And I think that's where analog devices comes in, because I mean, we do not do any GaN switches themselves. So what we do is drivers, and we do especially switching controllers that are optimized to work with GaN switches. And not necessarily do you need a switching controller optimized for GaN switches to drive a GaN. You can use standard MOSFET controllers in many cases. However, there is some risk that you drive the GaN switches correctly. And for that, typically a lot of discrete circuitry had to be used in order to reliably and efficiently, effectively drive GaN switches. And I think that pushed some people away early on from using GaN switches as their power switches. And our goal is with these new devices, GaN controllers like buck controllers, specifically designed to drive GaN, is to make life easier. And there are a few things that are necessary. So one important thing is a tight adjustability of the voltage. So that is important because the threshold voltages are just a little bit different in typical switching MOSFETs, and they have to be controlled better, these threshold voltages. And then you have to make sure that you don't have a voltage that's way too high, because if it's much higher than the threshold, GaN switches tend to break. I mean, any switch, also a MOSFET, tends to break if the voltage is too high, but the headroom above the threshold but below the absolute maximum voltage in GaNs typically is smaller than in switching MOSFETs. So that's an important thing, but there are other things too, like having a dedicated drive on pin and a drive off pin, like a positive gate current pin, negative gate current pin, would allow us just to make that to adjust the on transition separately from the off transition. And that's also a feature for GaN that's important, but for switching MOSFETs, not as important. And so these were just a few examples, but this, I think, is important. And I think now in the market, we see more and more specific controller ICs for GaN, and that makes life simpler, and that will help the success story of GaN switches in the market.
Okay, thank you very much. So I think we are ready for our next questions. And everybody can read that their question is as follows. What is the purpose of the substrate balancing circuit? How is Infineon solution superior to other vendors? Oh, whoa, whoa. We are really going for the extremes. But everybody can contribute. However, I suggest that Johannes will start at the moment.
Yeah, so the bidirectional switch is now a device that has one additional terminal, and that is actually the connection to the substrate. And it has two gates, right? And if one gate is turned on and the other one off, we want to make sure that, so to say, the second transistor that is monolithically integrated is really off, and needs to stay off. And in order to make sure that that also is facilitated under switching frequency operation mode, so continuous switching, one needs to stabilize this substrate. So that is important, because there's a backgating effect between these two, so to say, transistors that are monolithically integrated. And that is what we call the substrate stabilization circuit. The substrate stabilization circuit is critical in order to make sure that there is really a stable operation of this device under switching mode operation conditions. How now the Infineon solution is, how did you phrase it, is superior to competitors' devices? Our customers need to answer. We believe we have a very good implementation. It has been tested by our customers, and they say this is a very solid and stable implementation. However, what I want to say at this point in time, it's important that also other suppliers provide a robust solution here, because as we all know, single sourced products typically not that much appreciated by customers, especially if we want to go into high volumes. So I'm happy to see when also not just Infineon provides a very stable and robust solution here, but also other suppliers do so, because that will help to the adoption of gallium nitride.
Okay, I see Alex already waiting to say something. Do you want to add a direct comment, or shall we go to your next questions? What do you prefer, Alex?
I'm always, I smile a little bit when people talk about sole source and multi-source, because, Bodo and I have both been in this business almost 50 years. And when you're in the leadership position with the device and the technology, you're always in the sole source position. And everybody's trying to be the second source, and your customers want a second source. So I've fought that battle for 50 years, and I must say I prefer it to be in the position where people are asking me to get a second source for my products, because I'm in the lead.
Yeah, I like that wording. I prefer it to be in the lead. Yeah.
Me too. So definitely we want to be in the lead with the high voltage PDS. Yes.
Okay, but probably we should go a little bit back to the pure technology. And a question to Alex: what are the key challenges in implementing multi-level converters in server power supplies, and how does the GaN technology help to overcome them?
So, I think that, and by the way, I'm right now in Taiwan talking to customers about just that. I've been talking to customers all week long about exactly that question. And I'd say that the biggest challenge is, overcoming the comfort that people feel from a standard two-level topology. They know it, they understand it, they know how to design it, they know what's wrong with it. And so, what we've done is we've made complete reference designs, we write papers, we do documentation, but really it takes, I'll say a bold engineer to do something new. And that, I think, finding that bold engineer and the company that wants to take the risk is the key challenge. We've worked out most of the key challenges in terms of firmware and software solutions in partnership with Microchip. We've worked out, companies like Infineon have helped us work out isolated gate drivers and other infrastructural issues. So we've worked those problems out. Now it's time, hopefully, for a customer that wants to get ahead in this business to take the challenge.
Okay, but I would just like to add something. Everybody who wants to ask a question should please ask the question into the chat, and we will then raise that question later. But I already have another question for you, Alex. It's midnight, or is it 1 p.m.? Oh, 1 a.m. I don't know exactly. I really appreciate that you are participating here. So you need some more questions from us. How does the use of low voltage
keep me awake?
Pardon?
Just to keep me awake, huh?
Exactly. Yeah. You don't even need coffee. I really appreciate it. Thank you. So how does the use of low voltage GaN devices impact thermal management in high power applications?
Well, so, I don't think that, first of all, low voltage devices in high power applications, they like everything, they generate heat. Now, in a multi-level configuration, you have, I'd say more spreading of the thermal issue, and you also have the issue of isolating the various stages. So there's pluses and minuses. But low voltage devices in general don't have as much conduction losses, and therefore don't generate as much heat. And that's a positive factor. Not generating the heat is the easiest way to manage heat.
Yeah, that's right. A short question to Frederik in between. In which way do you think can an appropriate driving system contribute to better thermal management in high power applications?
Yeah, I mean, I guess most of the losses really come from the GaN devices. So in other words, if you have a good GaN switch that you switch quickly on and off, your switching losses are low, right? So this is giving, I guess, the main contribution to high power conversion efficiency. However, the driver strength, of course, has to be good enough and strong enough for the switch. Then also, of course, what's important just to drive the switch is a good board layout and all these things to avoid parasitic inductances in the drive path and things like that. However, that wouldn't really influence the efficiency all that much. So I guess the answer really is just to make sure that the efficient GaN is driven in a reliable and proper way, and the driver mostly contributes the drive current for charging the gate and for discharging the gate to turn it on and off quickly. However, that challenge is much easier with GaN because the gates are so much smaller than in a MOSFET, right? In a MOSFET, I think the driver strength was quite a bit more important to turn on the MOSFET on and off quickly as compared to GaN.
If I could just add one thing, you know, with the GaN devices switching so quickly, generally in the circuits we see, the magnetics are where the largest heat is generated. That's true in buck converters, where the GaN device is typically half the power dissipation that's in the magnetics, and in an LLC where it's also about half that in the magnetics. So there's a lot of work that needs to be done in improving magnetics if you want to improve efficiency.
Yeah, and especially in improving the size of the magnetics by using higher frequencies, I think.
Yeah, and you know, you go to higher frequencies, and then you have other issues with the efficiency of the magnetics.
Yeah, I also wanted to point out on in this regard that you know, especially low voltage GaN devices, they've been becoming so good that now the RDS(on) of those devices is in the order or even lower than the actual resistance of turn around the transformer in an LLC, for example. So
yeah,
you know,
so the resistance is coming from that.
Right. It gives you an idea of you know, how low the semiconductor or GaN power losses can be LLC converter, right? There are so many other components within that converter that start to contribute to the losses even more.
One comment from my side, Frederik, you indicated that, right, with parasitics, super important, of course, is layout. When we talk about discrete GaN and then a discrete gate driver, that the layout is really properly done, that you don't have a lot of current flowing over the source inductance, for example, or you create an artificially large source inductance that creates a feedback loop to the gate driver, pulls down your gate drive circuit. There you lose a lot of performance. What we are seeing is with moving to GaN, layer becomes super important and critical, that really the full efficiency is extracted from what the device can actually deliver.
I don't think that can be emphasized enough, you know, Johannes. You know, I visited hundreds of customers, you know, more than 100 every year. And, you know, in almost every case, a new customer with GaN has struggles with layout. Because you know, they're not used to the sensitivity to parasitic inductances in particular. We put a lot of tools on our website. There's a lot of papers written on it, a lot of FAEs out there. And if I could give customers, and I always do, one thing, I'd say, get somebody from you know, the GaN industry to check your layout, and you will save yourself a lot of trouble.
Fully agree, yes.
So yeah, I would like to say something about this too, and I completely agree that customers do have, or users of switchboard power supplies generally do have issues with board layout. However, it's interesting that with using MOSFETs as switches, also the board layout is extremely important, right? I mean, you have the high switching currents on and off. And if you take really advanced high power switching MOSFETs, they can also switch quite quickly, and within a few nanoseconds, depending on the voltage and current and everything, within a few nanoseconds you can switch on and off. And that so the challenge has been around for a while. But I do agree with your statement that it seems like it still is a problem, just like it has been 5 years ago or 10 years ago, outside of GaN usage.
So we had a question coming in from one of the Zoom users here in the chat. Do GaN switches legitimately, oh, what a word for me, add value to motor drive inverter systems? Who wants to be
Absolutely.
first?
Absolutely. I'm jumping out of my chair on that one.
We want to keep you awake.
So a few ways. First of all, let's look at lower voltages for a moment, where I have, my experience. If you are running battery operated systems, running motors, they tend to be 100 volts and less. And those motors actually operate more efficiently at about 100 kilohertz than at 20 kilohertz. Most of the motors are designed that way. But you can't go to 100 kilohertz with a MOSFET. So if you go to 100 kilohertz with a GaN device, the motor's more efficient. The GaN devices are fine at 100 kilohertz. But you also save about 7% of the power delivery cycle because you don't have dead time to deal with a GaN device compared to MOSFET. And at 100 kilohertz, you can throw away those electrolytic capacitors that you use in your motor drive circuits. And I think most people agree that electrolytic capacitors are about the worst component you can get. So we're seeing, for example, in humanoid robots and drones, in all sorts of battery-operated systems, people are going to 100 kilohertz, power tools, another example, 100 kilohertz, getting rid of electrolytic capacitors, and they have to use GaN at that. It's a very, very big advantage.
Yeah, and the same applies for high voltage. So we have a range of customers, including, for example, applications like inverters for washing machines or dryers or hair dryers or whatever you want to look at, where they clearly see a benefit when moving to gallium nitride. So what's typically used in these AC powered applications today is IGBTs on the inverters, creates huge amounts of losses. And when you move to GaN, the losses dramatically drop by 70, 80%. You can remove, for example, a heatsink, and overall system cost goes down. Yeah, and efficiency goes up exactly for the reasons that Alex already mentioned. And here you don't even need to go to 100 kilohertz. If you go from 10 to 20 or 30 kilohertz, you already see this huge advantage that the motor losses go down so dramatically without increasing the losses on the inverter because it's GaN. That you get the overall system benefit. So definitely we see a range of applications that move in this direction because of this excellent performance that GaN can also provide in motor control. So yes, legitimately, yes.
Well, I have another question. How is the high voltage bidirectional switch enabling new topologies or applications?
Yeah, so I would say the bidirectional switch can be used whenever, or it's actually ideal to use whenever you had a topology where you see two back-to-back switches, right? Because then we integrate this into one switch, as said before, it gets smaller, and typically also it's very cost efficient. So I would say it's not really about new topologies, but about making these topologies potentially more cost effective and with less components, so they become more attractive. One topology that is flowing around in the market since quite a while is what we also call a cycle converter, where instead of doing a typical PFC and an LLC or AC/DC and then DC/AC and an AC to DC and replication, instead of this two-stage conversion, you do a single-stage conversion with the cycle converter. And here, one needs this back-to-back switches, and here gallium nitride in this configuration as a bidirectional switch can actually be an excellent device. So this is used in, for example, or will be used very soon in solar microinverters. I think we will very soon hear more about that. We also have customers that work on that for onboard chargers. So this is a topology becomes super attractive now, where we have really a range of customers working on it because this bidirectional switch, for example, can replace two back-to-back silicon carbide switches, and that is then a very effective implementation. It's a bit more complex to do. Yes, one needs to learn a lot of new things, like Alex was already mentioned. New control schemes, new transformers are needed, gate drivers are needed, and so on. So the ecosystem also had to develop in order to make it happen. But I think now we're there.
So I would personally like to come back to the inductor size part. And one of the reasons is we have already prepared a question on that. The article written by EPC mentions that multi-level topologies reduce inductor size significantly. Something you didn't elaborate so far is on how this affects the overall system design and performance. Maybe you can tell us a little bit more about that.
Well, yeah, Alejandro, why don't you take a crack at it? I mean, there's a 9-fold improvement in inductor inductance, but why don't you explain where it comes from and what other benefits we get from it?
Right. So in a multi-level topology, we're talking now about, for example, a totem pole PFC, and how a multi-level topology affects the size of the inductor. So in a multi-level solution, the current ripple on the inductor reduces by a factor of the number of levels squared. So that allows you to reduce the inductance that's required to maintain a similar current ripple in the inductor. And because you're reducing the inductance now, you can trade it with lower DCR and smaller inductors as well. So from there you can imagine how that affects the overall size, and of course, if size and volume for the inductor are lower, cost will be lower as well. So you can see how a multi-level solution affects many aspects of a PFC converter.
So, for example, on a 4-level converter like we have in our article, the effective switching frequency is 3x. So each leg is 150 kilohertz. So it's really, the inductor sees 450 kilohertz, and it sees 1/3 the amount of ripple. Now, the inductor shrinks to 1/3 the size because of frequency, and then that shrinks another 1/3 because of the reduced ripple. That's where it comes in that squared factor. So now you have an inductor that's 1/9 the inductance. And the inductor is a significant resistor, and it goes down by 1/9. That's going to be a lot less resistance, and that will improve the efficiency of your system. But also, the inductor costs less than half because it's much, much smaller and lower inductance.
Okay, I think I have another question for you, Alex, or Alejandro. How do the design improvements in okay, yeah, I'm too far. Sorry, it's middle of the day for me, but sorry. With data centers increasingly adopting 48-volt architectures, how do GaN-based multi-level converters compare to conventional high-voltage silicon-based solutions in terms of adaptation and deployment?
Well, I'm out here in Taiwan because we want adoption and deployment. Multi-level solutions for servers are yet to be adopted, but because our solution is just now, and we've had a tremendous reception because there are very well-defined benefits. So, I've for years I've said, gee, GaN is going to replace MOSFETs. I believe that. And I also believe that at least in AC/DC solutions above 3 kilowatts, multi-level solutions will replace 2-level solutions. And that's just beginning.
Okay, so we are hopping, as you saw already. My next question goes most likely first to Johannes. It came from the chat. What type of current sensor would you recommend for double pulse test setups? Is a coaxial shunt still the way to go for fast switching?
So yeah, I have to admit I'm not the right person to answer the question. But if Alejandro is still here, maybe he's the right person here. I would refer to him. I guess he's more
Alejandro, do you have an opinion on that one?
Yeah. So, well, I mean, in our experience, at least for low voltage GaN, we have to say that we have not been able to measure current in a double pulse test circuit without affecting the switching transient. It's just, switching for GaN devices can be that high that it's very difficult to introduce in the circuit a current sensing element that does not affect the switching. So that being said, the best solution, for that need would be to use a shunt resistor and a coaxial shunt. I think that would be the best solution. But still, it will have an impact on the switching transient.
I know that in measuring the current in our LiDAR reference designs, what we do is we use massively paralleled, very low value resistors, surface mount resistors, and we mount them such that the foil is down on the board to reduce the inductance just going up into the resistor and back down. You can get effectively very, very low inductances, but as Alejandro said, it still impacts the circuit. It's still a significant parasitic inductance factor.
But for that, what I would say is for current measurement, of course, for current sensing, GaN offers this beautiful opportunity, what you can also do in silicon, but more elegantly, I think in GaN, that you integrate the current sense in the GaN switch, right? So I think we're all working on this kind of products, and there's huge interest from customers to get their hands on these products, because we can remove exactly these resistors that just add additional resistance in the power path, and again, losses that are not needed. So really, we can do lossless current sensing and enabling that in a wide range of applications from low voltage to high voltage. That's super interesting. And with gallium nitride, one can do this in a very effective way, always paired, of course, with the respective gate drivers.
And I think Navitas has some excellent products out that actually use that current sensing, lossless current sensing function. It's not purely lossless, but it's sort of a lot less than using a resistor.
Well, let's hop to the next question that we prepared. How do the design improvements in the EPC article, cover story in Bodo's Power Systems in March, align with the latest Open Compute ORv3 standard requirements?
So the article, which it was just part one that showed up, part two I think shows up this month. The OVR3 requirements are completely met. EMI, soft start, all the various OVR requirements are met by that reference design. That's mostly a function of firmware as opposed to the multi-level design all by itself. You can if you can get your hands on our reference design, you've got it right there.
Okay, so probably we should already now go to the next questions. It is, are there any specific reliability concerns when using low voltage GaN devices in high voltage applications? If so, how are they mitigated?
There are no special reliability issues. The GaN devices, basically, the low voltage GaN devices are used like devices that are low voltage in non-multi-level applications. So there's nothing special that impacts that could create greater reliability problems. Some people have said, well, but you have more components in a multi-level system than you do in a two-level system. And that is correct. So that you can look at that factor of more componentry as being a reliability question. But I also think that low voltage devices tend to be more reliable than high voltage devices, just because the stresses are less inside the device at lower voltages. So overall, I'd say it's probably neutral. Low voltage versus in multi-level versus two-level.
I have a quick question, if I may ask too. So, you said you could increase the efficiency, right? And that could mean that things might run a bit cooler compared to an alternate solution. That could help the reliability, I would assume, at the same power level, right?
Absolutely. Yeah, but
Interesting.
people tend to design things so that they, the power density goes up.
Okay.
And if
Yeah.
you improve efficiency, you squeeze it more to
Yeah.
get it back
That's
up.
true. That's true.
Yeah.
Good point.
And so you level out, but you have a higher power or
Yeah.
better form factor or
uh.
cheaper cooling and so on.
Yeah.
So
I mean, I just say about GaN, by the way, it's a very reliable component. The only wear out mechanism is thermomechanical. You're not going to see GaN fail or wear out because of anything other than thermomechanical stresses.
So the next question already popped up. What applications benefit from Infineon's high voltage bidirectional switches?
Yeah, so I would say those applications that move towards really high power, so this AI power supplies, for example, server power supplies, silicon power, onboard chargers, I think there this bidirectional switch can really provide benefit while the corresponding topology is, of course, chosen. In single-phase systems, for example, Vienna rectifiers could be used, or ARICs could be used, and here you have this back-to-back configuration that can be replaced by a bidirectional switch. But also in three-phase system, again, Vienna or T-type inverters could be used, and again, also here, the bidirectional switch could be used to replace the back switches. I think the benefit is, as already said, it's a reduced component count. You shrink again further a bit in size. Of course, the right gate driver components are super important to also have. So if you have a tiny semiconductor switch, but still a massive gate driver circuit around it, that's not super helpful. So therefore, also the right gate driver is needed. With GaN, you can get again then the usual benefits as we heard. Also for low voltage, you can go to the high frequencies, capacitive component size, you induct the overall system, and so on. So I think these are the key benefits, and I would say at this point in time, with the technology that we have, I strongly see it in these very high power applications. So onboard chargers, AI switch mode power supplies, whenever there's a topology used that really needs such a back-to-back configuration, then it makes sense.
So we are almost approaching the end, but I still have one question left for Alex. How do GaN devices perform under transient conditions and voltage spikes compared to traditional silicon MOSFETs? I think I know parts of the answer, but Alex, it's up to you.
So let's separate out the two types of transients that people are worried about. One is gate voltage transients, spikes on the gate, and the other one is drain voltage transients or spikes on the drain. In terms of spikes on the drain, voltage transients, GaN is well known to not have avalanche capability, and MOSFETs do. So what about that? Well, first of all, the GaN devices have a very large voltage margin. It's just intrinsic in the way they're built. So you can overvoltage the device and it will not fail. Up to many, a 100-volt device will probably, take over 200 volts without any problem. The issue with overvoltage on the drain is not that it fails the device, it's that it causes trapping. And it takes a few of those electrons out of the conduction path and your on resistance starts going up. So it's really a soft failure. And we've completely characterized that, by the way, in our reliability reports. So the good news is there's not a hard failure out there. Even if you go into full avalanche on a GaN device, it doesn't go into hard failure. It just, the on resistance starts going up a little bit at a time. Now on the gate side, the gates of the GaN device are not insulators. They're semi-insulators. They're actually gallium nitride, and it's semiconducting as well. So as you go to higher voltages, there's actually higher leakage current through the gate. So it has somewhat of a snubber effect on the gate voltage. But also with our devices, and I think with others as well, we have a lot of gate voltage margin to our maximum spec. And in our devices, we've characterized that, and now we've allowed for voltage transients to go up, well above the maximum voltage, so that if you have small spikes, you can, comfortably use the devices safely. That's not where we see problems. We have never, ever had a return from a customer or field failure because of a gate failure. That is not the failure mechanism. So there's plenty of margin there, in fact.
Okay, so thank you very much, Alex, for staying awake in the middle of the night for us. We really appreciate that. But I think now it's time for you to really go to bed because the next customer is waiting. Thank you so much. But not only thank you so much, Alex, also thank you so much, Johannes, and thank you so much, Frederik. And now I will turn over to Bodo, who will switch on his microphone before he will say bye-bye to all of you.
Gentlemen, have a nice evening beer or a midnight beer. I had all these little things left over from my sailboat, which I had also more than 30 years ago. And yeah, it's always a pleasure to have you in a fruitful discussion about technology. And I'm looking forward seeing you at PCIM in May. So enjoy life until PCIM. All the best. Bye-bye.
Bye-bye.
Bodo.
Bye. Thank
Thank
you.
you, Alfred.
Bye.
Thank you for participating.